In this video, we're going to explore one of the main applications of differentiation, and that is to find either the tangent line or the normal line. Let's get into it. The tangent to a function is a straight line which has the following properties. Firstly, it must intersect that function at a particular point. And lastly, it must have the same gradient as the function does at that point. For example, the tangent to f of x equals x squared at x equals 1 would look like this. We can find the equation of any straight line by using the gradient point formula. All we need to know is a point along the line and the gradient of that line. Using the criteria from before, the point along the line comes from the point at which you want to take the tangent at. In this example, we wanted to take the tangent at x equals 1, so the x-coordinate of that point would be 1. To find the corresponding y-coordinate, all you would have to do is then sub that back into f of x, obtaining y equals 1. Therefore, the point at which we want to take the tangent at is going to be 1, 1. All that's left to find is the gradient, which we know must be equivalent to the gradient of f of x at x equals 1. Remember, the derivative of a function tells us the gradient of that function for any value of x. So if we find the derivative of f of x and we sub in x equals 1, we will find the gradient at x equals 1. The derivative of x squared is just going to be 2x. Therefore, if you want to find the gradient at x equals 1, we know that the gradient is going to be 2. And finally, we just substitute back into the gradient point formula, since we have the gradient and the point. And when we do, we find that the gradient of the tangent is going to be y equals 2x minus 1. If you have a CAS on hand, then you can shortcut the entire process by using the tangent line function. All you have to do is give the name of the function, the input variable of that function, and then the x value at which you want to take the tangent at. Finding the derivative isn't the only method of finding the gradient. For example, if the angle that the tangent line makes with the x-axis is known, then that can be another method by which we find the gradient. The gradient of any straight line can be found by finding tan theta, where theta is the angle that the straight line makes with the x-axis in an anti-clockwise direction. For example, this angle would be considered pi on 6, not 5 pi on 6. It goes in the anti-clockwise direction, just like the unit circle does. Let's try an exam question where this was tested. In this question, we're asked to find the angle of a tangent line with respect to the x-axis in an anti-clockwise direction. Okay, well, the angle of a straight line is directly tied to its gradient. This tells us that the gradient of this straight line is going to be important. We are also told that this line is tangent to f of x at x equals -1. Therefore, the gradient of the tangent line must be equivalent to the gradient of f of x at x equals -1. This means, as long as we find the gradient of f of x at x equals -1, we can equate that gradient to tan theta and then back solve for theta. So, to find the gradient of f of x, we're going to first find its derivative by using the chain rule. Now that we have the derivative, we want to find the gradient at x equals -1. So, we're just going to substitute x equals -1 into the equation, and thus find that the gradient is going to be -1 on root 3. If you got this far, then the fact that this is an exact value should tip you off that some circular functions knowledge is required here. -1 on root 3 is a tan exact value, which first occurs when theta equals 5 pi on 6, and therefore that's going to be our answer. Also, if you're able to use the CAS in the exam, then you can speed things along by using the tangent line function again. All you have to do is just steal the gradient off of the linear term and then stick that inside the tan inverse. Finding the normal line isn't actually much different than finding the tangent line. We're actually going to use a very similar process. The only difference is, instead of finding the line which is parallel to the curve, we're going to find the line which is perpendicular to the curve. All that really means is that when we find the gradient, we're going to then find the negative reciprocal of that gradient, which just means we flip it on its head and then slap a minus sign out the front. Otherwise, it's all the same. If you're also studying physics or spec, then it makes a bit more sense as to why we would want to find the normal line, since it's used in calculating different types of forces. But if you're just studying methods, then really you just only have to consider it as another straight line equation to find. Let's try an exam question. Now, this was actually part D of a Tech Active exam, so there's a few key bits of information that were required from the previous questions that I'll just list out here. And sure enough, that actually completes step 1 for us. Next up, we just have to find the gradient at that point. Now, because this is a linear equation, we don't have to look very hard, since the gradient of a linear equation is constant regardless of where you look. And in this case, it's just going to be -2, the coefficient of the x. Now, we're just going to find the negative reciprocal by flipping it into a fraction and then multiplying by -1. And lastly, we're just going to plug in all the terms that we know into the gradient point formula. except this time we're going to use the negative reciprocal gradient. And just as a final tip, since this was a tech active exam, you can skip the entire process by just using the normal line function. It has the exact same syntax as the tangent line function. You just give the function, the input variable, and the x value at which you want to take the normal line at. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll send you to my website.